This is Chapter 4, Section 4, the last section in this chapter. So when we have a test on Monday, it is going to be over all 4 sections together out of this chapter. Starting off with this section, we're going to talk about everyday forces. Some of it you've already heard, like you've heard gravitational force. You know that's the force due to gravity. Weight is the magnitude of this force due to gravity. We were talking about weight right there, which is a scalar quantity, and you already know it changes with the location of the object in the universe. So if it's on the moon, is it going to weigh more or less? It's going to weigh less. Calculating weight at any location, you've already seen.
Boys and girls golf.
Maybe there won't be any more interruptions. Anyway, so force equals mass times acceleration. We've seen that formula. You already know acceleration due to gravity is 9.81 meters per second squared, and typically that's in a downward direction, so you would add a negative to work with that. This video is talking about comparing mass and weight. I don't really think we need to watch it. You tell me. It's going to talk about your weight on the moon. You've seen stuff like this already in chemistry. Your weight on the moon, do you know how much less it is than on Earth? It is 1/6. So on the moon, the force due to gravity is going to be 1/6 of whatever it is here on Earth. What about your mass?
Equal.
The mass is going to be equal no matter where you're at because it is not affected by gravity.
It gets smaller.
Hmm?
It gets smaller when I went to
Not mass, weight. Weight gets smaller.
I said I didn't get smaller when I go to the moon.
You. No.
I hope not.
Okay. Yeah. Normal force. We've already been introduced to the normal force, but we're going to show you another picture just to back up what you've already learned. But it is perpendicular to the surface that your object is on. I can't stress that enough. But it's not necessarily always opposite from whatever the force of gravity is. Force of gravity is always in a downward direction, but if your surface is at an angle, then your normal force is also going to be at an angle. And they give us a formula here. Your normal force is equal to mass times gravity times the cosine of theta. Mass times gravity times cosine of theta. Notice, if we were to continue to draw out that line, I'm going to do this in another color. This normal force right here, if you draw it out, notice it is at 90 degrees compared to where your surface is at. So you draw that line all the way to your surface, it is going to be at 90 degrees. The theta that you see there, that angle, how did that angle relate to maybe something else that we had seen earlier? I told you if you took your normal force, went straight up and down, and then you had the force of gravity off in this direction to try to get, let's say you had another force pulling in that direction, so then that force is there. Just to get as many components along the traditional XY axis as possible. What's the translation for your angle that you see? This angle right here, how would it translate? Yep. That angle right there is going to be the same as whatever the angle of your incline is. Do y'all remember us talking about that? Okay. Anybody have any questions so far?
When talking about forces, the word normal means perpendicular, and it always indicates the direction that is perpendicular to the surface of contact between two objects. Consider an object resting on a flat surface. The external force of gravity is acting on the object. The object is not moving down, so there must be another external force acting on it. This is the reaction force of the surface on the object. In this case, the normal force is exactly opposite to the force of gravity. But as the inclination of the surface of contact changes with respect to the ground, the normal force is no longer in the exact opposite direction of the force of gravity.
Pretty much what we've already talked about. Now we're going to add in a couple more formulas that deal with friction. You've got two types. You've got static friction and kinetic friction. Static, the key to this one is this is a force that resists the initiation of a sliding motion. So this is going to be, you've got two objects that are in contact. They are stationary or at rest to each other. So how can you overcome that initial rest position and get your object to start moving? And then you've got kinetic friction. What does the word kinetic mean? It means movement. So once your two objects are actually moving against each other, a tire against the road, you rolling your pencil across the desk, after there's already motion involved, it's the force that's going to oppose the movement that is already there of your two surfaces that are sliding over each other. And it tells you in that last bullet point that kinetic friction is always less than your maximum static friction. I want you to think of an example of if I asked you to move your chair across the floor, push it across the floor. Don't you have to give it just a little bit hard of a nudge just to get it started? And then it's a little bit easier after that? You've probably had examples like that you could think of. A book, if I asked you to slide a book across your table, the initial nudge or force that you have to give it is a little bit more than once it starts going, it'll just keep going.
More difficult to move an object across the surface of another object. Surface texture, electrical attraction, and other forces that push objects together all affect the friction experienced by the objects. Even if the surfaces of two objects appear to be smooth, they are rough on a microscopic level. In general, as the roughness of a surface increases, the friction increases, and more force is required to move the object along a surface. Even the surface of fluids, such as water and air, can cause friction. The reason swimming provides such a good workout is that you must exert force to overcome the friction created by water molecules. Electrical attraction also plays a role in friction. Pushing a strong magnet across a refrigerator door requires more force than pushing the same magnet across a wooden table. The greater the attraction pushing the objects together, the more the objects resist movement, and the greater the friction. On the other hand, if the electrical attraction is negative and the objects repel one another, friction can be reduced. Maglev trains take advantage of this phenomenon to give a smooth, nearly frictionless ride.
Have y'all heard of a maglev train before? Huh? Yeah. Okay. If you haven't, then basically you've got a rail that has magnets on it that has the negative side of the magnet. The rail that is on the bottom of the actual train itself also has negative magnets on it. What happens when you put two negative electrical? Yes, they're going to repel each other. And it happens in a series. You don't just have negative and negative and it's not on constantly. It is something that can be charged to be on or off. So if you had your maglev train and you had, your train here, you've got your rail right here at the bottom, that is something that you can turn on and off as the train is moving in that direction. It's a way to propel it. So you'll turn one section on, then you'll turn your next section on, and then your next section on. So it's a constant on-off motion of these magnets to help propel it. And that's also, you can make it go forward or reverse. You just turn them on in the reverse order to get them to go in reverse.
Gravity can also push objects together. The heavier the object being moved across a flat surface, the greater the friction due to its weight. Similarly, if we push down when moving sandpaper across a piece of wood, we increase the force pushing the surfaces together and consequently increase the friction.
So if we look at these, the three main things that created more friction. Do you remember what the first one was?
Surface texture.
Okay. It has to do with your surface texture. So the rougher your surface is, then the more friction you're going to have. What was the second one we talked about? Electrical attraction. So the greater your electrical attraction, the more friction you'll have. Okay? So if you've got something with a positive charge and a negative charge, you know that they want to attract each other. So you're going to create more friction. And then what was the third one? It's the weight of your object. So heavier objects are going to give you more friction. So it's going to be pretty easy for me to move my book across the floor, but if I take one of your tables, your lab desk that you're sitting at, and try to move it across the floor, it is much heavier, so it's going to be harder to move, and it's trying to overcome the initial static friction there. More free body diagrams. You are going to be drawing free body diagrams as you're going through the different examples that we have. The force of your kinetic friction, and again that is friction that is moving, is always opposite the direction of your motion. So whatever way your object is moving, kinetic friction is in the opposite direction. You can even take that with your cars that we talked about. If your car is moving in this direction, then your force due to kinetic friction is going to be in the opposite direction. Also, your force of friction is always parallel to your surface of contact. That's a really easy one. If this car is on the road, then force due to friction is parallel with the road, just opposite direction from the direction that you're moving. And then to get your static friction, you're talking about objects that are in equilibrium, your frictional force point in the direction that results in a net force of 0. So let me circle that for you too. For static friction, it's going to result in a net force of 0. It's a direction that gives you a net force of 0 for your static friction. So let's give you two equations to help you calculate kinetic and static friction. So the little U symbol that you see there stands for coefficient of friction. For kinetic friction, you've got your coefficient is equal to the force due to kinetic friction over your normal force. And I know on mine it looks a little bit weird, so I'm going to rewrite it for you. And then for static friction, what do you think that term is supposed to be that's in the numerator? Okay. Does it show up on y'all's?
Yeah.
Okay, good. So that's really supposed to be f of x max. And again, that's going to be right before your object starts moving. And again, it is over the normal force. Normal forces are perpendicular to your surface. What about units? What are the units going to be for your coefficient of friction? If it's force divided by force, the units are... What's the unit for force? So what happens when you have Newton divided by Newton? It's going to cancel out. So your coefficients are going to be unitless. You don't run across that very often, but in this case they are unitless. This right here is showing you tables that give you several different objects, steel on steel or glass on glass, ice on ice, wood on a wet snow, and so on and so on. But it gives you the coefficient for static friction and the coefficient for kinetic friction. And like we've already pointed out, what do you notice about the two? Static friction is what as compared to kinetic friction?
Always higher.
It's always higher. It is always higher. What about this? Rubber on wet concrete. They don't have anything there for static friction. Or waxed wood on dry snow. Why do you think they don't have anything for static friction? It's going to be basically negligible. That's it. I mean, have y'all ever, how many of y'all have driven when it's raining outside and, I had a bad experience on my bicycle with it on wet pavement. That was not fun. Not fun at all. The brakes, they helped none. And they could even put on their skin on wet concrete. There's actually not as much friction there either. I don't think I bled at all, but it sure did hurt. And I'm sure that I went at least 15 feet sliding along the concrete. Okay, waxed wood on dry snow. That's when I was younger. I don't do that stuff anymore. Yeah. I wasn't even doing anything special. I just, was going to lock up my brakes, and the bike went one way and I went another way. Yeah. Let's move on. So here's a sample problem right here. You can see there's lots of stuff going on. We even have an angle that we're working with, pulling this box of books. I don't know that any of us would choose this particular method of transportation, but it'll work for us to get all of this in here. It is a little bit of a long, drawn-out process to get the answer, and then we've got air resistance we're going to talk about after this. So, a student attaches a rope to a 20-kilogram box of books. He pulls with a force of 90 newtons at an angle of 30 degrees with the horizontal. The coefficient of kinetic friction between the box and sidewalk is 0.5. Again, that's a unitless number, and it wants you to find the acceleration of the box. So, you can leave your PowerPoint on that one, and I'm going to go ahead and we're going to try working this out. Starting off with everything that was given. What was the first thing that was given? What was it? Is that weight? That is mass. 20 kilograms. What else was given? Okay. Pulls with a force of 90 newtons. We have had lots of labels on forces. It can be normal force, gravitational force, force due to static friction, force due to kinetic friction, or even some other force that might be out there. How do y'all want to label that force? It says he pulls with a force of 90 newtons. You could call it force due to pull. What? Force the rope. We're going to go over an example after we get done with this. There is a difference whether you are pulling an object or pushing an object. Okay? And we'll go over that after this is over with. So, they call it force applied. It does say that he pulled. We're going to go ahead. I'm going to put down APP for force applied. And again, this is a pulling force, which we'll treat a little bit different than a pushing force. We do have an angle of 30 degrees. It's important that you label that 30 degrees properly. Coefficient of kinetic friction. What symbol do we use for that? UK. And it wants us to find the acceleration of the box. Okay? So that's not acceleration due to gravity, it's the acceleration of the box. And I know in your PowerPoint, the first thing they do after they label everything that's given and what you're looking for is they're going to draw out what exactly do we have. So let's go ahead and draw it out. Here's my box. Okay? What kind of forces do we have on the box? We have an obvious one that is the force applied that's 90 newtons and he's pulling it. So if we go with a traditional XY axis, this is at 30 degrees. Think about the picture that's on your PowerPoint. Above or below the horizontal? Above. So we have a force in this direction. That is 90 newtons, force applied. And the angle that we're working with is 30 degrees. What other forces do we have?
Gravity.
Force due to gravity. And what direction should that go?
Straight down.
Straight down. Any other forces? Huh? How do you know there's a normal force?
The gravity has to cancel out.
Okay, so you got to have a force that is pushing back up on your box. There's your normal force. Any other forces? We're going to have one due to friction. You know, they give us a UK right here, and you already know that that's due to friction, so what direction is that?
Opposite.
It is opposite of, if he's pulling the box, it's going to be opposite of that direction. But it is parallel to your surface, so that is not at 30 degrees. That one is going to be parallel to your surface. So that's the force due to kinetic friction. Any questions on how we've labeled anything? Now, let's talk about how, let's say you get this far and you feel comfortable with the point that you're at right now, and you've got to solve for acceleration of the box. What has to happen at this point? What do we have to do with all these forces?
Find a net.
Find a net force, okay? That means you need everything, components in your X direction, and you need all the components in the Y direction. And, you know, force due to gravity, that shouldn't be too big a deal. Your force applied, though, we don't have components in X and Y, so you definitely want to start there and get your components in your X and Y direction. That way we have everything along the axis, and then we can work with that. So let's go back and we'll work with our applied force. How are we going to solve for the X and Y components of it?
Right.
Yep. You've got your 90 newtons, which is really your hypothesis. Solve for the X and... No. Hypotenuse. I wouldn't have even thought anything of that had you not said that. Your hypotenuse. And use sine or cosine to find the other part of this. So force applied in the X direction, and then you got your force applied in the Y direction, if you're looking for those. What are we going to use to find for the one in the X direction? 90 newtons times what?
3.
If I think about my sine and my cosine, sine is what? Opposite over hypotenuse. That one is adjacent over hypotenuse. So for your X component, is the 30 degrees opposite or adjacent? It's adjacent. So you're going to say times cosine of 30 degrees. And we'll do just the opposite for the one in the Y direction, for the sine of 30 degrees. And when you calculate that out, you should get in the X direction 45 newtons, and in the, wait, I wrote that backwards. Yeah, that's our Y direction. Y direction is 45 newtons, and in the X direction, you've got 77.9 newtons. Any questions on how we set this up? Okay. What do you think we should do next?
See what forces we can cancel out.
Okay. See what forces we can cancel out. Do we know the normal force yet? Nope. Do we actually have calculated the force due to kinetic friction? we've already calculated the force due to kinetic friction, Fk. I see UK, but I don't see Fk. So we're going to actually have to go find Fk too. Looking in the PowerPoint, here's what they're going to have us do after this. First step, they label it A, B, and C. So for A, we want to find the sum of all the forces in the y direction, and it tells us that needs to be equal to 0. Why equal to 0?
It's not moving up or down.
Right. In the y direction, there is no movement. So those need to be equal to 0. We talked about the second thing they're going to want us to do, which is find our Fk. What formula are we going to use to find the force due to kinetic friction?
UK equals FK over FN.
Okay, UK equals Fk over Fn. If you rearrange that, then now it's going to be UK times your normal force. Do you realize there in Part B why you have to do Part A? Because what does Part B use that we don't have a number for yet? What do we use in Part B that we do not actually have a number for yet? The normal force. So that's why you have to go through and find the sum of your forces in the y direction, is because you're going to find your normal force in Part A so that you can turn around and use it in Part B. So that's why we have to do that step first, and then we'll do Part B. And then Part C, after you find Fk and you find your normal force and you've got your other forces, we'll figure out what Fg is also. Then we can go back and look at the sum of the forces in the x direction, and this is where the acceleration comes in. So mass times acceleration in the x direction, and that Ax is what we're trying to solve for, because that's what the question asks us to find. Any questions right now? Okay. Let's go look at Part A. I'm going to move on to another slide. So Part A is finding the sum of all of our forces in the y direction. Do we have the force due to gravity? No. Okay, remember, we've got Fg here, we've got our normal force here, and then we had also just solved for the y component of our applied force. What was the y component of the applied force? 45 newtons. Okay, so we're going to end up having to find the normal force. So what else do we need to find before we can find the normal force? What do we have to find before we can find the normal force? Force due to gravity. And what's the formula for the force due to gravity? Isn't it just mass times acceleration due to gravity? Okay, so plug in your mass. That was given as 20 kilograms. Acceleration due to gravity, 9.81. So your force due to gravity is going to be equal to 196 newtons. So we found F of G. What's that?
Why is 9.81 negative?
And this, well, it'll all wash out. Just keep watching. I'm not saying it's not negative. It'll end up being negative. You can go ahead and put the negative there. It's not going to matter. So when we find, it's because it just shows direction, right? It shows direction here. So then when we find the sum of our forces, all of those are going to be in the y direction. We know we want it to be equal to 0. So in the positive direction, you've got your normal force, which we don't know. We also have the 45 newtons in the positive direction. And in the negative direction, what do we have? Force due to gravity, which is, if you add it on, then you get back to why isn't it negative? Really it is, because it's in a negative direction. Subtract the 196 newtons. So from this point, you're going to solve for F of n. Can everybody solve for F of n? You can just take that off, because all of that is going to be equal to 0. Y'all said it was 151 newtons. Your normal force is going to be lower than the force due to gravity whenever you have some type of pulling motion on your object. Do you know why that is? If you're pulling on an object, why are you reducing your normal force based on what gravity is? Yeah, well, it doesn't even have to be at an angle, but you're taking basically some of the weight off of whatever that object is, which is just another force. It is accounted for in another direction, but it's going to be less than force due to gravity. So your normal force is 151 newtons. What did we say we were going to do after that? What was part B? What was it? Okay, so we're going to find our FK, right? So for part B, we're going to find FK, which is equal to UK times FN. UK was given as 0.5. FN we just solved for, that was 151 newtons. So the force due to kinetic friction, which is what? 75.5 newtons. And you got to think that is in a negative type direction also. And then part C, this is where we're trying to find the acceleration. And to do that, we've already taken care of everything in the y direction. That is equal to 0, but we needed our normal force to go with what is in the horizontal direction. So F of x, that is going to be equal to your force applied, because that was in a positive direction, and that's only along the x-axis. And you're going to subtract off force due to kinetic friction. Why are we subtracting off force due to kinetic friction?
Because that small part of it cancels out small part of the force applied.
That's right. It's in the opposite direction. So subtract those two numbers for me. That was, what, 77.9 and 75.5? What is it? I'm hearing 2.4. Did we have 75.5 or 75.6? Okay. It's okay. So 2.4 newtons, that's what's left over in the x direction, which means your box is actually accelerating and moving, because there is a force left over when you find your net force. But we said we needed the acceleration, so force is equal to mass times acceleration. So 2.4 is equal to mass, which was 20 kilograms. And find the acceleration in the x direction. What is acceleration in the x direction? You should get 0.12. Meters per second squared, give it a direction. It's going to the right or in the direction of where you're pulling. Again, let me add something real quick to this. It was what we were just looking at. Keep in mind, because you will have some questions that go back and forth with this information. That was us talking about an object being pulled. Whenever you have an object being pulled like that, and in this case, you can tell that it was at an angle, your normal force is going to be less than the force due to gravity. But if you have an object in which you are pushing, okay, your normal force is actually going to be more than your force due to gravity, because think about it, the normal force, it's what's pulling back up your force due to gravity there. You're adding an additional force in the y direction, okay? So let's go back to the PowerPoint. Talk about some air resistance. So looking at air resistance here, we've neglected it for the most part up till now. It is a form of friction, and it says whenever an object moves through a fluid medium, fluids are gases or liquids. So gases and liquids both fall into your fluid category. It says air or water, give you two examples. You have to account for the fluid of resistance to the object's motion. Talking about falling objects, because if you're falling, and if you're talking about here on Earth, it's probably falling through air. The upward force of your air resistance balances the downward gravitational force so that your net force on the object is zero. When this happens, that maximum speed that you reach before you reach an equilibrium point is called terminal speed. You've probably also heard it called terminal velocity too. So if you fall out of, say, an airplane and you're plummeting towards Earth's surface, you are gaining speed up until a point, but there will be a certain point at which the force of gravity pushing down on you is going to be equal to the force that Earth is pushing back up against you. You don't just keep accelerating to infinity, okay? You do bottom out at a certain point. So that's called terminal speed or terminal velocity. We've already looked at fundamental forces. I think that we talked about these in either the first or second section of this chapter. You do have 4 fundamental forces. These right here are your different field forces. Now, the majority of the time, your field forces happen over a distance, okay? But occasionally, you can have a force through direct contact that is still considered a field force, like if a magnet is directly touching the object that you're wanting to change. But there you go, your electromagnetic forces. This is some information that would have been in the book, but I'm going to give it to you now. These are microscopic interactions. Microscopic interactions, and it does typically occur over large ranges. It does typically occur over large ranges. I mean, you're probably thinking about magnets that we sit here and handle and touch, but are there other electromagnetic forces supplied by different rays, frequencies of light, things like that, that might happen over a large area? Like the sun, okay? There is a force that's applied with that too. Gravitational force is going to be the weakest of these forces that you see here, whereas the strong nuclear forces is going to be the strongest. These right here, the strong nuclear forces, that's what's going on within the nucleus itself. Those are very strong forces to keep all of those protons with like charges housed within a very small area, so it is the strongest. And again, these two right here occur over very small ranges or distances, you know, because you're talking about the size of an atom whenever you look at these 4. Guys, we're going to end up working through both of these examples, number 3 and number 4, right now. So right now I want you to work on number 3. Remember everything we've talked about. It's going to take you multiple steps to get to the answers that they want. So don't think this is just plug in one calculation into one formula and be able to solve. So number 3 is the one you're working on right now. So adding to this, hold on. So add to your regular homework that 4th question. I will add a picture of what is up here on the board to go with question 3 as far as how we answered all of it. Question 4 is going to be a little bit different because in question 4, You got a box that is being pushed. So you are going to go about it just a little bit differently. And you also have an angle with which it's being pushed across the floor, and the floor is considered to be horizontal.
Will I be posting anything?
No, I want you, well, this is in the podcast, so if you go and visit the podcast, you can get to this question, because this is being recorded. And I will also post a picture of what you see over there.
And you said Flexbook page 180, 118B, and what number?
1 through 5. I don't think so.
Well, they're only missing today.
It's that, I think that one's been easier so far. That one's been easier than 30, but I just looked at it again and I don't know.
Oh, yeah, the podcast. That's all we have.
I'm kind of lost.
Y'all can figure it out.